We're in section 10.3 now. Going to talk about arc length and surface area with parametric equations.
Isn't it basically the same equations, but instead of dy, dx, we do like dx, dt?
They're similar, but there's a couple of differences. So on Friday we did a short derivation to come up with our formula for surface area. We used our expression for surface area in rectangular coordinates with y as a function of x, and substituted our expressions for x and y as functions of t, and came up with our arc length. We said S was the integral from a to b of the square root of f prime of t squared plus g prime of t squared. Where x equals f of t and y equals g of t are parametric equations. And a is less than or equal to t, less than or equal to b. So this was the arc length from a to b of our curve. We said that the curve doesn't intersect itself except at the endpoints. And this is, oh, I forgot my dt here, didn't I? So this is how we're going to find our arc length, and we'll also use this to come up with our surface area. So let's just do a quick calculation with excuse me, with this formula, and then we'll apply that to surface areas of revolution. Does anybody need any reminders of how we came about this when we went through? All right, and I will just to reemphasize, we do have to be careful that our curve, occasionally we have to be careful that our curve doesn't intersect itself except at our endpoints. We want to make sure that we're A and B, that our curve isn't crossing itself somewhere in that interval. So let's take a look at a quick example. And some of us commented on this on Friday. We want to find the length of x equals cosine to the third of t, y equals sine to the third of t for 0 less than or equal to t less than or equal to 2 pi. And this curve is called an asteroid. And it comes out, just a quick sketch, it comes out looking kind of like this. And these should be symmetrical here. But it looks kind of like that. And this would be, for this particular curve, we'd have 1, we're up here at 1, -1, and -1. So we're going to, what we'll do here is we're just going to find the length here in the first quadrant and multiply by 4. Since our curve is symmetrical, we'll just multiply by 4. So we need to come up with our pieces to put into our formula. So dx dt, and we need that squared, is going to be 3 cosine squared t times minus sine t. That's our derivative, and we're squaring that. And when we square it, we end up with 9 cosine to the fourth t sine squared t. And we do the same thing for our derivative of y with respect to t, and we're going to square that. We get 3 sine squared t times cosine t for our derivative, and we're squaring that. And we get 9 sine to the 4th cosine squared t. So we get to, this is what we end up putting into our radical to find our arc length. So, our arc length is going to be, we're going to look at, actually before we start plugging into our integral, let's just calculate what our radical is. So we just want to find our radical of the square root of this plus this. So we want, we have the square root of 9 cosine to the 4th t sine squared t plus 9 sine to the 4th t cosine squared t. So we're just going to work with this for a minute. How can I simplify this? The sine squared and cosine squared, we can factor that out, right? So what do we end up with? 9 cosine squared t sine squared t times cosine squared t plus sine squared t. So I just factored out a sine squared, cosine squared, and 9 cosine squared sine squared. Sine squared t plus cosine squared t, thankfully, is 1. So we end up with 9 square root of 9 cosine squared t sine squared t, which simplifies to 3 times the absolute value of, oops, I forgot my t here, cosine t sine t. Now in the first quadrant, we're looking, we can check our parameters. We go from x equals 1 to x equals 0 on the interval from 0 to pi over 2. And the absolute value of cosine t sine t is on 0 to pi over 2 is positive, so we don't have to worry about the absolute value there. So this is just 3 cosine t sine t for 0 less than or equal to t less than or equal to pi over 2. So we're just taking that first quadrant and we're going to integrate that and multiply by 4. So our arc length, finally, so s equals 4 times the integral from 0 to pi over 2 of 3 sine t cosine t dt. This is a nice, easy u substitution. I can say u is sine t and du is cosine t dt. So this equals 12 sine squared t over 2, evaluated on 0 to pi over 2. And when we evaluate that, we just end up with 6. So the arc length of that asteroid is 6 units. Questions on that? And we're getting a little practice in here with sines and cosines because we'll end up using sines and cosines a lot when we work with polar coordinates. All right. So surface area. Surface area of revolution when we have parametric equations. we're just going to extend our arc length formula just like we did previously with arc length. So surface area of revolution. So just make a quick sketch here. So we have some curve like so, and we're going to revolve this about either the x or the y axis. So we have, just like we've been talking about, x is some function of t. We have parametric equations, y equals some other function of t. Doesn't cross itself on a to b. So we're talking doesn't cross itself on the interval that we're interested in. If we're going to revolve it about the x-axis, our radius of revolution is just y. And if we're going to revolve it about the y-axis, our radius of revolution is just x. So what we're doing with the formula, just as to remind ourselves, is we're looking at this little piece of arc here. We'll call it ds, little piece of arc length. We're revolving that around the x-axis or the y-axis, and we're summing those little pieces of arc length. So we end up with a tiny little piece of a cone. So we end up with a tiny little piece of the side of a cone. And our equations come from the surface area of a cone. So we're thinking of adding up those little pieces of arc length as we revolve around the axis. So our equations: surface area of revolution. We have capital S is what we usually use for surface area of revolution. 2 pi, the integral from a to b of g of t times the square root of f prime of t squared plus g prime of t squared dt. And this is for revolution about the x-axis. So our radius is y, is g of t. The 2 pi, that accounts for the fact that we're going around, revolving around in a circle. And this is the square root of f prime squared plus g prime squared dt is our little piece of arc length. So we're taking that and we're summing that over our interval as we revolve around the x-axis. And if we revolve around the y-axis, our surface area, 2 pi, integral from a to b of f of t times our radical f prime squared plus g prime squared dt, and this is for revolution about the y-axis. So often what we do with these is, if we think of this radical, this square root of f prime squared plus g prime squared dt, if we think of that as our little increment of arc length, and we call that ds, and we call this g of t or f of t, that's our radius of revolution. We can write this, often we write this in shorthand. We say that our surface area is 2 pi times the integral of r of t. R of t is our radius times ds. So r of t is the radius of revolution, and ds is this radical, is our little portion of arc length. And we'll see this, an expression very similar to this a lot when we start talking about 3 dimensions, when we start working on that next semester. So we can think of f of t as, or g of t as our radius of revolution, and ds is this whole thing is our little increment of arc length, our little piece, arc length differential is what we'll end up calling it. And as you might guess, these integrals can end up being very messy and difficult to evaluate. All right, questions on this? So let's look at a quick example and then we'll be done today. We want the surface area of revolution of the portion of the circle x squared plus y squared equals 9 from (3, 0) to 3/2 3 square root 3 over 2, revolved about the x-axis. So we have several things that we need to do here. So let's draw a quick sketch here. I'm a big fan of drawing sketches. So here's a sketch of our circle. Nice round symmetrical circle there. And we're revolving about the x-axis. So we're going this way, and we're going from here, this is 3, 0, to up here at some point 3/2 3 square root 3 over 2. So we just want to revolve this section about the x-axis, so we'll have a little kind of sideways bowl-shaped thing. So first off, we're talking about parametric equations. So we want to come up with parametric equations for this circle. How would we write a set of parametric equations for this circle? X equals 3 cosine t, and y equals 3 sine t. So if we square x and square y, x squared plus y squared, we end up with 9. And we have our x associated with cosine, so that when theta equals 0, we're out here at 3, 0. So that's going to be our parametric equations for our circle. And we will become very familiar with this type of parametric equation. So there's our equation. We have our coordinates here expressed in terms of x and y. So next we need to express them in terms of t. So when x equals 0 corresponds to t equals, or I'm sorry, when x equals 3 corresponds to t equals what? T equals 0. And when x equals 3/2, we have 3/2 equals 3 cosine t. So cosine t equals 1/2. And this corresponds to t equals what? Pi over 3. So our interval in terms of t is going to be from 0 to pi over 3. So we're going to, now I'm just going to plug into our equation for our arc length. Our surface area, or not our arc length, our surface area, S, is going to be 2 pi. The integral from 0 to pi over 3. Our radius of revolution is what about our y-axis? 3 sine t, it's y. So our radius is 3 sine t. And then we have this big radical, x prime squared and y prime squared. So we have minus 3 sine t squared plus 3 cosine t squared dt. And thankfully this simplifies nicely. So we end up with 2 pi, the integral from 0 to pi over 3 sine t. What does our radical simplify to? 3? Because we have a 9 sine squared and a 9 cosine squared. Sine squared and cosine squared are 1. Take the square root of 9, we get 3. So we end up with minus 18 pi cosine t evaluated on 0 to pi over 3, which comes out to 9 pi. So our arc length, or our surface area of that surface of revolution is 9 pi square units. Questions? All right. Homework. There you go.